Let's talk about RC circuits today. That is to say, a circuit that has both a resistor and a capacitor in it, along with a battery. And let's look at how they behave as compared with circuits that have only resistors in them or only capacitors. With a circuit with only resistors has a constant current going through. So you can calculate the current going through any number of resistors in the circuit, and even though it may be different from resistor to resistor depending on the configuration, the current will remain constant for all time, well, as long as you have the battery on. In this case, though, with a capacitor, that changes things. That's a situation where the current is going to change and the charge on the capacitor will change with time, and we'll show you exactly how that happens. So let's start with a very simple series circuit with a battery with an EMF script E. I have a capacitor and a resistor C and R values, and I have an open switch at the beginning of the problem. So right at this time, there's nothing flowing through the circuit because the battery isn't engaged. It's an open circuit. Now, let's say in the next instant at t equals 0, let's say, we close the switch. Now current is going to start to flow through the circuit. But what's going to happen is this, at least qualitatively, almost instantaneously, current will flow through the resistor, and at the start, or almost at the start, we'll talk about that when we talk about magnetic fields. But for all intents and purposes, we'll say at the start, the current will be full through the resistor, and the voltage drop across this resistor will be, so at t equals 0, roughly. The value of the voltage across the resistor will be just what's coming out of the battery. The value of the voltage across the capacitor will be 0 at the very beginning, as soon as the switch is closed. The current through the resistor then will just be equal to E over R. The charge on the capacitor will be 0. So this is all initially. But as time goes on, the capacitor is going to charge up. As it charges up, there's going to be less current going through the resistor, until finally, at some later time, we'll call it t later, figure out what that is. The voltage across the resistor will be 0, the current in the circuit will be 0, the voltage across the capacitor will be the voltage coming from the battery, and the capacitor will be fully charged, and so we'll have a value of C times E. And what we'd like to do is see how that transpires in time. And the way to do that is we can take advantage of Kirchhoff's loop rule. So if I go around the loop, like so, I can write this as E, battery, minus voltage across the resistor, minus the voltage across the capacitor equals 0. Kirchhoff's loop rule. So the voltages around the loop is 0. And in this case, Q and I are going to be instantaneous values. So we said at t equals 0, I will say that I naught is equal to E over R. That's the initial current in the circuit. And then, as we said, at some time we expect it to develop so that the capacitor gets fully charged. Well, what we'd like to do then is to play with this equation a bit. I have too many variables in here to begin with, but I can write the current as a time derivative of charge. And so I can rewrite the loop equation as E minus R dq dt minus, I'm going to use little q here because we're going to let, if big Q is the total charge, let's let little q be the charge with time, charge as a function of time equals 0. And I can move things around. I can say dq dt is equal to e over r minus q over rc. We have a differential equation. And there's one of the simplest techniques for solving a differential equation is to use separation of variables. If you can do that, that's a fairly easy way to solve a differential equation. In this case, we want to get all the q's on one side and all the t's on the other side. And when we do that, you'll get dq divided by q minus ce is equal to minus dt over rc. Well, at this moment, what we want to do then is integrate. So I'm going to integrate both terms. I'm going to integrate my charge term from charge equals 0 to fully charged. Let's call that q. And I'm going to integrate my time term from 0 to some time t, that time when it's fully charged. So if I do that, I integrate the left side, I get the log of q minus ce divided by ce is equal to minus t over rc. And then I want to exponentiate. So I get, if I do e to the log of this, I just get q minus ce over ce is equal to e to the minus t over rc. Another way of writing that is to say then, if I put in my limits, q is equal to, I should say, q as a function of t then can be written as q times 1 minus e to the minus t over rc. And I can write that q will be, of course, when it's fully charged, c times e. 1 minus e to the minus t over rc. This is the equation for the charge in a charging capacitor. So the capacitor has 0 charge to begin with, and now I'm charging it. I close the switch, and the charge on the capacitor increases with time in an exponential fashion. The current then, I can take a time derivative. The current as a function of time looks like then, I can write this as e over r, e to the minus t over rc. So you have an exponentially decreasing current through the resistor while you have this increasing charge on the capacitor. And so these are the two expressions. We often call RC, we define that by a tau sub c. This is called the capacitive time constant. It's just the product of R times C. And as you can see, it's kind of interesting, but if I take the product of ohms and farads, I get seconds. And if I were to plot the charging capacitor, it would look something like this. When t is equal to tau sub c, and again, this is time, and this is, let's say, voltage across the capacitor. Well, let's say just charge. Charge as a function of time. We find that at maximum, it's going to be c times e. When the time is equal to the time constant, the capacitor is 63.2% charged. So we can say that Q is equal to 0.632 times Q max, or C times E. You also notice that it essentially takes an infinite amount of time to become fully charged. If I let t go to infinity here, this term becomes 0, and then of course I have C times E. Now, for all intents and purposes, if you wait about 5 or 6 time constants, the capacitor is fully charged. So that's kind of a nice graph. Notice too that the current is going to be an exponentially decreasing function by the same token. And so we can do an example of this. Suppose I have an RC circuit where I have the following configuration. I have a 5 microfarad capacitor. I have a 12-volt battery. Here's my switch. And I have a resistor 8 times 10 to the 5th ohms. And I want to find the following. I want to find the time constant. I want to find the maximum charge when the capacitor is fully charged. I want to calculate the initial current. I want to find Q as a function of time. I want to find the current as a function of time. And I want to find the current at the time constant. And the charge at the time constant. So immediately, tau RC can be written as the product of R times C. So it's 8 times 10 to the 5th ohms, 5 times 10 to the minus 6 farads. And so that gives me a time constant of 4 seconds. Maximum charge is going to be equal to C times E. So that's going to be 12 times, this is 12-volt battery, times 5 times 10 to the minus 6 farads. That's going to give me 6 times 10 to the minus 5 coulombs, or if you like, 60 microcoulombs. My initial current, of course, is going to be the voltage divided by the resistance, and that's going to be 12 divided by 8 times 10 to the 5th, or 1.5 times 10 to the minus 5 amps. My charge as a function of time, I can write as my initial, my maximum charge, which is 6 times 10 to the minus 5 coulombs, times 1 minus e to the minus t over RC. My current as a function of time, I can write as E over R, which is 1.5 times 10 to the minus 5 amps, times e to the minus t over RC. And at tau, when Q is equal to tau, if I put my value for tau in there, I will get a charge of 37.9 microcoulombs. And if I put the value for, if I want to find the value for current as at t equal tau, that will give me a current of 5.52 microamps. So these are real simple problems that you can do using an RC circuit. Now, that's half the story. Suppose I have the complete opposite situation. Suppose I've fully charged a capacitor, and now I remove the battery, and connect the capacitor to a resistor and close the switch. This is what we call the discharging case. The capacitor begins to discharge through the resistor. So initially, we may have had some, let's say that the initial charge is Q, and the voltage across the capacitor then would be Q over C. Over time, what's going to happen is there will be discharge of the capacitor, you get current going through the resistor, but you will have dissipation through the wires and through the resistor of a certain amount of energy. Let's show that. We'll apply Kirchhoff's rules again. In this case, I have a simpler equation. In this case, I can just say IR is equal to Q over C, and replace I by dQ dt times R is Q over C. If I separate variables again, this is going to be a simpler expression. I'll get dQ over Q is equal to minus dt over RC. I can integrate both sides. I get log from zero, I should say from Q initial to 0. This will be from t equals 0 to t equals t. Notice what happens in this case. On the left side, I get log Q. I should say Q to, let's call it little q. Can't say 0 because I can't do the log of 0. So I'll get the log of Q is equal to minus t over RC. If I exponentiate, I'm going to get that I can write Q as a function of time is equal to my initial Q times e to the minus t over RC. If I take the time derivative, my current as a function of time is going to look like, just like the last case, the charging case, I'm going to get I naught e to the minus t over RC, where I naught is e over R, or whatever the voltage across the capacitor was initially over R. So you can see in the discharging case, both the capacitor and the resistor, the charge on the capacitor decreases exponentially, as does the current in the going through the circuit and going through the resistor. And of course, the question is, where does it go? Where does the energy go? And of course, it's dissipated as joule heating through the resistor, possibly through the wires as well, but generally through the resistor. And we can talk about that by examining the energy in a capacitor. There are a couple of ways to do it. One is fairly straightforward. Another way is maybe a little bit more elegant. So let's talk about energy loss in a resistor. So let's say I have a 5 microfarad capacitor and it's charged to 800 volts. And then I discharge it through a 25 kilo ohm resistor. The question is, how much energy is lost to joule heating? In other words, how much of the electrical energy is converted to thermal energy? Simple method is to say, well, when I begin, my initial energy is going to be equal to 1/2 times C E squared, or 1/2 C V squared in this case. And that's going to be, if I put my numbers in, that'll be 1.6 joules. Right, because I have 5 microfarads 800 volts. That's going to be E. Well, if that's my initial energy and I end up with no energy at all, I can say, well, of course, all of it has been dissipated. I lost 1.6 joules. And you would be correct. But it might be interesting to see another way of showing this.
We have 6 minutes left, Dr. Blows.
That's good. Good. So at the beginning, we have an expression for the energy that looks like this. And at the end, we will end up with, of course, 0. I can write energy as power times time. And so I can write this, my energy, as the integral of I squared R dt from 0 to infinity. I can then write my equation as R. My current squared is I naught times e to the minus t over RC. E to the minus 2t because it's squared. dt, 0 to infinity, which I can write as I naught squared R, 0 to infinity, e to the minus 2t over RC dt. I squared R constants, I naught squared. I can write this more properly as take the limit as, let's say k, we'll just use k, goes to infinity of the integral I naught squared R, integral 0 to k, e to the minus 2t over RC. When I do that, I'm going to get, when I integrate that, I get e to the minus 2t over RC times RC over a minus 2. So I'm going to take the limit as k goes to infinity of minus r squared I naught squared c over 2 times e to the minus 2k over RC minus 1. Notice what happens. Take the limit as k goes to infinity. This term goes away. And so what I end up with is I naught squared r squared c divided by 2. I naught I can write as e squared over r squared. This becomes r squareds go away. I end up with 1/2 c e squared, which of course was the energy for the capacitor. So it works the same way. This is a more around the world way of getting there, but it's kind of nice to see that you can do it through power dissipation as well as just saying, well, I start with this amount of energy and I end up with this amount of energy. So that's a nice way to look at how we talk about the dissipation of energy through a capacitor, through a resistor, I should say, in an RC, in a discharging RC circuit. And that's all we have for RC circuits. The next topic that we'll cover will be magnetism and magnetic fields.